So hi everyone, welcome to the first webinar for this year under the ISPRS Student Consortium webinar series. So based on the survey that we conducted last year, our members voted on deep learning as the next topic in this webinar series. So for today's webinar, our moderators will be Charmaine Cruz, our newsletter editor-in-chief, and for everyone who is following our social media accounts, our other moderator is Dr. Mustafa Osuner, our social media coordinator. So let's start the webinar, and I pass it on to Charmaine.
Okay. Okay, so hello everyone and welcome to today's webinar. So I'll just be giving a short introduction about the Student Consortium. So about the ISPRS SC or the International Society for Photogrammetry Remote Sensing Student Consortium. So it's the official representation of the youth to the ISPRS community. And the main purpose of this ISPRS Student Consortium is to link the students, young researchers, and professionals from different countries who are interested in the fields of remote sensing and photogrammetry. And of course, it aims to provide a platform for exchange of knowledge and information across this group. And the ISPRS Student Consortium has been organizing different events and activities which are dedicated for the students that will integrate them effectively into the ISPRS community. So here are the current board members of the ISPRS Student Consortium. So we have Cheryl, the president, Charles, the vice president, myself, the newsletter editor-in-chief, Mustafa, the social media administrator, and Sona, the board member. So one of the main activities of the student consortium is the summer school. So basically, it aims to provide an opportunity for the students and young professionals to participate in a series of events and lectures at minimal cost. And of course, to provide them an avenue to expand and establish their professional networks. So last year, there were 4 summer schools conducted. So there were in Uganda, Poland, South Korea, and Brazil. So for this year, there are 3 scheduled summer schools. So there's one in Brazil, one in Turkey, and in France. Another one is the newsletter. Newsletter is the main publication of the student consortium. So for this term, we have already published 13 newsletters. So they are all available and uploaded to our website. So you can find the link over there. And we have upcoming issues. So for this month, we'll be publishing a newsletter which focuses on climate change. And then there will be one about 3D GIS and BIM, and of course, a special issue on the ISPRS Congress. So during the ISPRS Congress in June, so there will be a 3-day youth forum, so which includes technical sessions, which are dedicated for the students. And here are the other main activities of the student consortium for the students. So we'll be having speed dating, youth forum technical sessions, special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, general assembly, student night, summer school, and mapping party. And here are our social media accounts. So we have Facebook, Instagram, and Twitter. So all the information and details regarding the summer school schedule, travel grants, publications, and other opportunities for the students are posted in our social media accounts. So, of course, the webinar. So, basically, the main aim of the webinar is to disseminate information and knowledge within the ISPRS Student Consortium group. So, it also acts as a way of connecting the group, the member of the Student Consortium, with the wider ISPRS community by inviting them as our lecturers for our webinar. So Mustafa will give a short background about the webinar's theme for today.
Thank you, Charm. And hello, everyone. Welcome our webinar series today. And in 2 months ago, we just created a poll on social media, and we just see the great interest into the deep learning, and therefore we decided that the webinar for deep learning, especially for the area of photogrammetry and remote sensing, would be the great interest and would be attract many people. And therefore, in today, Dr. Konrad Schindler will give us a lecture on deep learning for photogrammetry and remote sensing. As you all guys just interested in deep learning, you possibly heard the term before. And what could I say is like the deep learning is one of the intelligent algorithm capable of solving complex problems. Over the past couple of years, deep learning showed great aspect in research and industry like medicine, like robotics, computer vision, and particularly smart processing of images and videos. And today, Dr. Konrad Schiller will give us a lecture on deep learning for photogrammetric analysis and remote sensing. And right now, I think Dr. Konrad Schiller can start his lecture. And thank you for giving us this lecture, Konrad Schiller. And it's your turn.
Thank you.
Okay, I'm sorry. So just a few reminder before we get started. So just a few guidelines for our attendees. Okay. I'm sorry. Okay. So we'll be having a 1.5 lecture proper. And then afterwards, we'll be having Q&A and a short summary at the end of the webinar. So by default, all attendees are on mute as they join. So of course, this is to avoid interrupting our lecturer and other attendees. There will be a Q&A session after the lecture. So there's a Q&A box in your control panel. So it's located at the bottom of your control panel. So if you would like to ask questions to Dr. Schindler, please use that box. Just type the question and we will be notified by then. But please make sure that your questions are short and related to the topic. And in any case that our lecturer will ask question during the lecture, you may answer by pressing the raise your hand button. So it's also located in your control panel. And once the question has been answered, you can press the lower your hand button. And at the end of the webinar, so an evaluation form will be sent to you. So please complete the form. So now we can begin. Our lecturer for today is Dr. Konrad Schindler. Dr. Konrad Schindler is a professor at the Department of Civil, Environmental, and Geomatics Engineering, Institute of Geodesy and Photogrammetry in ETH Zurich, Switzerland. He has completed his PhD in Computer Science in Graz University of Technology, Austria in 2003. Since then, he has published numerous papers on photogrammetry, remote sensing, computer vision, and image interpretation. He has received several Best Presentation Awards in various conferences and honors from international societies, including the UV Heleva Award from ISPRS in 2012 and the MAR Prize Honorable Mention from the IEEE Computer Society in 2013. So without further ado, I will turn over the time to our lecturer, Dr. Konrad Schindler.
Okay, so thank you very much for the introduction.
Thank you.
Thanks for having me here. I hope it will be interesting. I'll just need to share my screen to start the lecture. Okay, so the topic that I was asked to talk about is a sort of an introductory lecture to deep learning in the context, of course, of remote sensing and photogrammetric image analysis. Let's get straight into it. You obviously have all heard of the great successes of this technology in the last years. On the slide, I mean, you know that, probably know that AlphaGo, that famous software that beat the world's best Go player to judge the position, so to look at the Go board, which is a raster and therefore basically an image, and decide what is the evaluation, what to do in a certain position, or how good is a certain position. It actually uses a neural network. It has some more technology to search for some positions that it can put in the evaluation, but the evaluation function is actually a deep neural network. Also here on the top right, I don't know whether you recognize this person here. That's the CEO of Google, Sundar Pichai, who's announcing the voice assistant a few years ago, and also that voice assistant that is built perhaps into your phone or into your computer actually also is a deep network that takes the sound signal is converted to something image-like as well, to a spectrogram, and then passed through a network to understand the words. And another big thing, another example where we've had a lot of PR in the last years, although it's flattened out a bit, is autonomous driving. So a special form of robotics where a vehicle is supposed to drive out on the road, take over the role of the driver, and therefore, of course, has to interact with its environment and needs all this sensing with cameras, with LiDARs, and with other sensors to see what's going on around it. And these vehicles actually have big deep learning engines in them. They even have dedicated hardware in them and extra batteries and stuff like that. So that's how it started. It got sort of omnipresent. And of course, since images are one of the main success stories, and we are all interested in images of the Earth mainly, we should maybe look into it. So in the geospatial sciences, it's especially a powerful tool for various data analysis tasks. It's sort of an all fits one engine if you have the data. So it is a regression system, a classification system, also a clustering system. One example that's prominent is, of course, just land cover mapping. So turning images into thematic maps, like on this slide. This is, by the way, not a hand annotated map. This is actually what you see here. This here is automatically generated by a deep network from the image besides. Okay, then let's get to the technical part. I'm not sure, I'm assuming that the audience have sort of a little bit of background in mathematical modeling, but nothing specific in machine learning. Is that about correct? Or would somebody want to raise their hand and tell me that I'm wrong? I really should cater to the right audience, so it would be good to know if I'm completely off. Okay, we'll proceed. And if I'm too fast or too slow, if the content is either boring or unintelligible, somebody please raise their hand and tell me, because it's very hard for me to judge if I can't see the faces and can't interact with the audience. So we'll start from very simple, basic estimation techniques that you probably know. For example, if you have a continuous quantity, something like a temperature or a coordinate, you could do a linear regression. So you can take some numbers that you've observed, some measurements, put them in a linear function, so basically just a weighted sum, and then you get an output. That's what's written here. You could also have another problem where you need to classify, like here. So you have to tell two different classes. This could, in an image, for example, be, is it water or is it not water, so that you can detect the water surfaces. And then this linear regression won't do, because water or not water is a binary variable. It doesn't live on a continuous scale. So you have to somehow convert this continuous number to a sort of a probability, a number that can only be 0 or 1 or something in between if you're unsure. And this is done by a function that's called the sigmoid function. That's this here. So this function becomes 0 to to one side, 1 to the other side, and in between it has a smooth transition. And if you map this linear expression through that function, then you get the answer. These two are very similar methods, obviously, and in the language of neural networks, you would call them both instances of a perceptron. So that's what I've depicted here. The perceptron, it's nice to depict it graphically. It takes the input variables, the observed values, something like could be pixel brightnesses, it could also be other things. So it takes input values and weighs them, so it multiplies them each with a weight. The weight is the function parameters that you fit to optimally fit this function, and then you get the weighted sum, and then you pass that weighted sum through some function. This is a general function, so this can also be nonlinear, to get the output. If f is just the identity, if it's not nonlinear, but just keep the same thing, then it's, for example, the linear regression. If you put there the sigmoid, it becomes the logistic regression. Okay, a little note on notation. For convenience, when we take this vector of our observed values, of our inputs, I will always add a 1. So this is a virtual number. This is just, there's always an observed 1. And this is only so that we can subsume the constant offset, the bias that we would have to add to the values inside this vector multiplication. That just simplifies the notation, because if here in this x, the last component is a 1, then I can have one weight, theta 0, that corresponds to that 1. And then if I multiply them together, it's 1 times theta 0, and I have the constant offset integrated. So that's just a trick. Okay, this perceptron is very simple. And now to build a neural network, the simplest neural network that you can build, except for the perceptron itself, is the so-called multi-layer perceptron. So the idea is very simple. You take such a network, you create multiple outputs. So you just have not only one set of weights that create one node here, but you have a second set of weights that make another node, a third set of weights that make another output, and so on. Each of these is again passed through this possibly nonlinear transformation function, through this activation function as it's called. And then you have a new vector of numbers, the black dots here. And these are before, then comes the activation, and you get a new set of numbers. So this is the output. And rather than saying, now these are all our outputs, we stick those again as inputs into a next perceptron. So we basically stack those in layers. And then the second one will create an output in exactly the same way. The math is not so important. I put it on the slide for completeness. So now the weight vector, this theta from the previous slide, this here, becomes a matrix because it's a stack of several vectors, one for each of the output nodes of the first layer. Then you multiply those with numbers, you get the outputs, you pass it through this activation, and then that one is again weighted with a second set of weights, and that creates the output. The one here in the middle that is marked in blue is then called a hidden layer, because it's sort of a latent hidden representation. What you see is the inputs, what you get are the outputs, and those values are in between. They have some sort of a way of representing the input better to make the output, but they don't really have a meaning. They are just some latent representation. The activation function, by the way, this F0 or F1, should be non-linear to make any sense, because otherwise, if you multiply these two together, you get a new linear weighting. So then it would actually just be a redundant way of representing something simpler. There was already a while ago a theoretical result that said one hidden layer is enough to approximate any function fairly well if it's wide enough. And there's the problem. That layer would possibly have to be very wide enough. And since we are dealing with remote sensing, so we usually have not one output, we have many outputs, possibly for every single pixel we want an output. We can extend this by just making also the last layer of this multi-layer perceptron such that it creates multiple outputs. It doesn't have to be the same number, but it could be the same number as the inputs. So we have not only one set of weights, but we again have a second one to create another output, and a third to create another output, and so on. So in principle, these are sort of independent MLPs, but they do share all the previous weights. Only the last layer does something different, which means that you could see this thing before the last layer as a sort of an internal representation that is common to all the different outputs, and that then just has to be weighted differently. So that's a general multi-layer perceptron, the sort of vanilla simplest size of a neural network. And a deep neural network is just the same with more layers. So there's no magic to that. You just, instead of stacking 2, you stack 3 or 4 or 5 or 6, as many as you like. If you stack more and more of them, there are 2 issues. You get more and more parameters that are unknown, more and more weights, theta, that you have to learn. And it also becomes increasingly difficult to learn if you don't do it right, because the distance between the input and the output just increases. But funny enough, while it would seem like that, in practice, it shows that having narrow networks, so the layers not so wide, but deeper, actually greatly empirically improves the parameter learning in practice. How that is done, we'll see in a moment, and makes these things sort of more well-behaved if you have the computational power to deal with them. And that's one of the reasons for the rise of deep learning, that we were lucky in that the rediscovery of it was driven in a good part by the greatly enhanced parallel computing abilities of GPUs, of graphics cards. So now we have a deep network. It's really just a stack of these simple linear combination followed by nonlinear transformation. Then we come to this transformation. So the transformation can be different things. In principle, you can stick many things in there. There are a few standards. Historically, one would actually really use a lot this sigmoid function that you see here, that ranges from 0 to 1. So you can interpret its output as a sort of probability. But in fact, that is not such a good function, numerically speaking, for inside the network. People then move to other things. There is, if you want this two-sided saturating function, you can, for example, take a hyperbolic tangent. What is the most popular and best working today are actually variants of this so-called ReLU, the rectified linear unit. So it's a half-wave rectifier. Any number that's positive just stays as it is, and every number that's negative is just truncated to 0. And that has the advantage that on one side, namely the positive one, the gradients don't saturate. If you go further out, you still get the same gradient, and you know in which direction to change it to get better. Only on the last layers, we still often use sigmoids because we need something that resembles a probability. Okay, so I think the model is clear. So everybody understands this stack of just linear perceptrons with a little transformation per element in between. So that will be our model. On the left side, we stick something in image analysis, often pixels, pixel values, and we pass them through this network. So we multiply with the weights, get something new, multiply the new thing with the weights again, and so on. And in the end, we get an output that we desire. So that could be, for example, a class in a map. That could also be some regression value like a biomass or vegetation height or something of that sort. If you want to look more into photogrammetry, you could also put in 2 images. Then it could actually be something like a stereo parallax, a disparity or depth or something like that. Okay, before we go on at this point, are there any questions about the model itself? Is there something unclear or something that we should talk about more? Doesn't seem to be the case. Okay. So now that we have a model, the next question is, how do we learn that model? Learning means nothing else than fitting its parameters, estimating the optimal parameters so that the model makes good predictions. It's a supervised learning method, so we're assuming we have pairs of what goes in and what should come out, training examples, reference examples, which we can use to learn those parameters. So the unknown parameters are the weights, all these many weights in the network. And it actually works, as you know, from probably parameter estimation or algebra classes. So you create an error function, you write down a mathematical equation that tells you how wrong you are. Basically, you pass something through the network, you look at the answer, compare it to the answer that you're expecting, that you want to get, and the difference between those two is the error signal that you try to minimize. Depending on the task, is anybody asking something here? No, okay. Depending on the task, you can choose different loss functions or error functions for regression. So if you want to predict some continuous quantity, it would often be the average distance between the prediction and the correct answer, so something like a squared error or maybe an L1 error, so an absolute error. For classification, the typical error function would be how far is the deviation between 1 and the predicted probability of the true correct answer. So you want the true answer to be predicted with probability 1 and the others to have 0. And the further you go away from that, the bigger is your error. So that means in the last layer, you have to have a transformation that makes these probabilities. It's called the softmax. It's basically something like this sigmoid for every class. And now we have also an error function. So now we can let the tools of mathematics play. We can use a minimization technique to minimize that error function as a function of the parameters, and that will give us a good parameter set. For neural networks, that's a bit more difficult than for other functions because this function is actually not convex. It has many, many local minima. You can only do local optimization. And the way it is done is gradient descent. So you look in which direction you have to go to make the error smaller. How do you have to change all the parameters a little bit to decrease the error? You take a step in that direction and you keep going like a rolling ball on this cost surface, on this error function surface, which is of course much higher in dimension in reality. That technique, if applied to neural network, is called backpropagation. So backpropagation, which is a bit of a magic word nowadays in the literature, is simply gradient descent in a neural network, or gradient computation, actually, not even the descent. So what you do is you take some example, you apply the net to it, run it through the network, you look at the answers, you compare them to the correct answers, you calculate the deviation, and then you propagate that deviation from the output backwards through the layers to all those weights, and see how do I have to change them a bit to get better. In reality, you don't do that every time for all examples. That would be too costly, but you do what's called stochastic gradient descent. So you simply sample a random small batch, push it through the network, create a gradient, which is of course much noisier and approximate because it's only from a few examples, but it's good enough. You improve the network a bit, and then you take another random batch, and over time, over the many batches, this thing will even out and give you a good optimum. In practice, this computation is of course done in one for the entire batch. So you push the whole batch forwards through the network, and the whole batch then goes backwards to get the gradient. Like the gradient is per batch, so it happens by itself. And these calculations can be parallelized very well because you do exactly the same thing at every neuron of a layer in parallel. You apply the same function, the same data types, and therefore you can put this on GPUs, on graphics hardware, and that is what makes these things fly. Otherwise, they would be too slow. I'm not going to go through it in extremely much detail, but I have it in the slides, so I want to show it. There is a worked example, if you like, a baby example for this backpropagation. So what it is the chain rule of differential calculus that we all learned at some point in high school, that if you have a nested function, f of g of x, if you want to compute its gradient, its differential, you can take the f, you can differentiate the f with respect to g, and then the g with respect to x, and chain those together. So here's a little example with some function. And the neural network is just a very, very big nested function. As you've seen, as you remember from the previous slides, it's just, you do the first layer, on top of that you do the second layer, around that you do the third layer, and so on. So it's a big nested function, and you do exactly the same thing. I'll run you quickly through the toy example. So here's my toy example. This is a very small network. It has 5 trainable weights in red. These are the unknowns. And we have an example, a training example with these values. They're blue. And the output that we would like to get here is 0. At the bottom, I put all the gradients, all the differentiation of all these functions that happen inside the network, just to make sure that you don't have to look them up. So what we now do is a forward pass. We take the input here, multiplied by the corresponding weight, do the same here. This weight contributes twice actually to 2 inputs. This is just for fun. It wouldn't have to be that way. We multiply them, then we take these values, we add them. So 4 plus 2 is 6, 6 minus 2 is 4. Then we pass them through our ReLU, our rectified linear unit, for example, which keeps those values unchanged because they're positive. We multiply again, we add them again, and then we apply a sigmoid. So first we do this 1 plus e to the minus x, and then we take the inverse. And the output that we get is 0.88, so that's not very good because we wanted 0. And now comes the backward pass. So that's how the learning works. You ask, how do I have to change the previous value, the input to that last node, to compensate, to decrease that error at the back? And you can compute that analytically if you know the differential. So you would basically say, what is the number that I have to multiply with this gradient, with this -1/1 to this value, to get -0.88, so to decrease this. And if you calculate that, you find it's 1.14. These two just happen to be the same. That's not. And then you go one step further. And again, to achieve that, how would I have to change the value before? You get the differential of this function, e to the minus, here's the weight 2. You want to get the 1.14. How do you get there? You have to put minus 8.4 into here. And then you keep doing that. If there are two branches, you just regard the other as constant, and so on. You keep doing this to the whole network, and then you end up with these values. So these are sort of the supposed corrections to get to where you want to be. Of course, you can't do them immediately all in one, because the function is not linear, so the gradient is a tangent approximation. You should only take a small step. So the small step is usually much smaller, but here I use 0.1 of the gradient to visualize it more easily for this baby network. So we change those values which we can change. These are, of course, only the red ones, the tunable function parameters. And we change them by 10% of this correction that we found here. So here it would be 0.84 negative, here it would be 0.56 positive, and so on. Then you get these new weights, so I've updated them now. And if I do a new forward pass to the network now, you can follow that up if you like, you end up with 0.51. So we already got closer to 0. And if we now keep iterating and doing that multiple times, now we back propagate again, then we forward propagate again, we will eventually get to a good result. So we will get a set of red weights that, if supplied with typical inputs as we see them, will give the correct answers. So that's how you learn. That's the optimization procedure. There are some extra tricks. Instead of this elementary gradient descent, so just take the old one minus some small reduction factor times the gradient, you can have momentum. So you say, like a rolling ball, there's basically a mass. So you keep going in the direction in which you were already going before. You just add the new gradient in a weighted form together with what was the previous one, so that this trajectory becomes faster and smoother. And there are even more, say, advanced variants. Usually they are the way of making it better consists in trying to find either more momentum so that you go faster, or another way of doing it is actually try to adapt the step size a bit more aggressively, not just keep it small, but try to find out from the behavior of the function whether you can increase it or you have to decrease it. Okay, so that is the whole principle. Yeah, there is some regularization very often, so you try to keep the weights small as well, so that you don't have individual weights get very big and they completely dominate the function. To regularize, to make the function smoother. So if all the weights are smaller, the function is smoother because it has less leeway to wiggle in response to anything. It's closer to constant, basically. And that can also be done. So that's just a term in this penalty, in this loss function, that says the parameters should also be small. Yeah, normalization is typically applied. I don't think I have to tell the geomatics people among you that if you do numerical calculations, you should normalize values. Normalization in this case often means center them around 0, sometimes maybe also normalize for the spread so that the variance is sort of standardized to 1. And in this way, everything's numerically well behaved and lives on the same scale. So this learning process, this takes a long time, because you have to show many examples, compute many gradients until those weights, which are initialized in some random manner, get to a good configuration. And here is a bit where the black magic lies. So sometimes you hear people say that, well, these things are difficult to train, it takes experience, you don't know how to do it. And that is really that you have to supervise this procedure. It's not black magic, it's not so difficult. The recommended procedure is that you have your training set and you also have a validation set that you don't use for fitting. You follow how this error function behaves on the two of them, and that will give you signals whether it's doing well or not. So a good learning rate slowly and steadily decreases the error very far. If you set it too high, it might go down faster, but then saturate very quickly and not get better because it takes two big steps and it doesn't really find the good minimum. If you take it very, very high, it might even diverge. And too low is also not good. So this is a bit difficult. There's no clear rule for that. Usually you start with some standard value and you follow it. Often also you actually stop in between, decrease the learning rate and keep going on a bit. So you're in this green regime, and when you see it flattens out, then you decrease it and you go down more and so on. This is the one point here where really you have to try a bit and gain some experience. We can't have a programming class here to try this out. That doesn't work in the short time of the webinar, but there are many excellent resources on the internet, tutorials to try. If you're new to deep learning as a framework, as a software environment, I would recommend Python. There are others that are equally good. There's TensorFlow and so on, but PyTorch seems to be the one that is at the same time I find the most convenient for learning. It's the most intuitive one. And on the other hand, it's also industry strength. You can do really good things with it. Okay, that was so far all about multi-layer perceptrons. I want to show you an application example, and it's not from imaging because MLPs are not used that much there. This is an example that those who are in surveying or geodesy might know, the computation of the tropospheric path delay. So when you use a GPS, a GNSS antenna, you're receiving signals from satellites in space and basically measuring runtime via the propagation speed of the electromagnetic radiation, the speed of light, and that speed of light depends on what's in between, on the material through which it passes. So it is influenced by the atmosphere. And this delay, this sort of deviation from the speed of light that you would assume that is caused by water vapor and other things in the atmosphere is called the tropospheric path delay. And to estimate that, you can, for example, use a neural network. So you take the data from the nearest meteor stations, the nearest weather stations, which you see on this map, they are the blue ones. Take the three nearest, for example, and they say, where is it? So the position, easting, northing, and elevation. You take the pressure, the temperature, the water vapor content, and these values, and you take the position of your receiver. And then you pass these values, this gives you 27 values or something, into a neural network with quite a few nodes actually. So you see the number of unknown parameters, and it's on the order of 1,000 even for this little problem. And the output value that you want to predict is the so-called zenith total delay. So this parameter that tells you how much the radiation was slowed down and delayed. And from that, then of course the path coordinates and so on, the station coordinates and so on. And you see actually that surprisingly here in this diagram, green is a physical model, a standard model, physics inspired model, but a standard model that is often used for correcting those delays. And a colleague of mine tried to use a neural network instead to learn to predict those delays from the meteor conditions and the position. And it turns out that by doing so, you can actually reduce the uncertainty almost by a factor of 2. Okay. So we've finished the general neural network topic. Are there any questions on this? Somebody wants to raise their hand? What questions do you have for me?
It seems there is no question in the question and answer part. Therefore, maybe you can continue, and then afterwards, if they have question, maybe they can ask. So maybe it's better.
No problem.
Thank you.
Good. So now we come to convolutional neural networks. So that's the specific type that is most useful for images. So the problem with this MLP that we described so far is that the number of parameters, of course, grows very quickly as you stack layers. You have a complete set of connections from every node to every other one. So it's quadratic in the size of this layer. If this is the size of the layer, is the number of pixels in an image patch, it's very many. And you are somehow not accounting for the fact that image statistics are shift invariant, as they say, which means that if you shift the image, if you look in a different position, then on average, the statistics could be the same, because you never know which bit of the image appears where if the viewpoint changes. So you exploit that spatial structure, that things are sort of local and shift invariant. And that works in this way, that rather than connecting every input node in a layer to every node in the next layer, what you do is you only take the nodes here in a neighborhood, in a spatial neighborhood, like a kernel, a filter kernel around every point. You put some weights in this kernel, so you multiply those with weights that need to be learned again, that are function parameters, and create the output. And you use only in this small neighborhood, so the connectivity drops a lot, because every output here is connected only to a small region of the input and not to all of them. And on top of that, you say that since we're shift invariant, since everywhere the same operations should give the same outputs because the statistics are sort of locally the same, what you do is you use the same set of weights for every 3x3 neighborhood. So what that means is, and that's where the convolutional comes from, this weighting actually becomes a convolution operation. You have a little kernel, like a filter kernel, that you pass over the image from one pixel to the next, and at every position from its neighborhood with the same weights, with the same filter, you compute the output. And of course, you can use multiple filters, and that will then mean multiple layers of output at every position. And if you stack that deep, it just means you make more of those again. So you do convolution of the image. After the convolution again follows again some nonlinearity, typically the rectified linear unit, so the clipping of the negative values. And then you do another set of convolutions. So here, for example, you take an input with 3 channels. You take a convolution with 64 outputs. So you create a 64 channel image of the same size. At every position, you have 64 outputs. Then you do the same again. And then you can add additional functionality into that network. One is pooling, so downsampling. You don't do this at every position, so you somehow average or pick values with a certain step size, usually 2, to make the layer smaller. That means that sort of the image is reduced. It's like an image pyramid. You get a bigger context, and then you keep going again with convolutions, you make it smaller again, and so on. And then the very end here, this end of this long pyramid, you can regard as an abstraction of the image, as a sort of a feature representation of what is in the image. And with that, you can then do whatever you want to predict, so that you do with normal MLP. Here you add what's called a fully connected layer, 1, 2, 3. And these are actually multi-layer perceptrons. So these are simply connecting everything to everything so that you get the global picture. But the important thing is this convolution. So you take the input, which is a 3D tensor. So it's x times y, the image coordinates, the image spatial extent times depth, the number of channels. And you run a 3-dimensional convolution filter, so a box of weights that you slide over there and apply at every position to get a new output. And you do this with multiple different sets of weights, so you get a new image that again has multiple channels, usually more than the input in the beginning. So this linear filter gives you a new raster image, and you can apply that to get the next level and stack those. For completeness, I've drawn this for an RGB image for you here with some example filter kernel, just to illustrate the convolution, but I guess you know how this works. So there is a little box of, in this case, 27 weights. Each number is multiplied with the weight that corresponds to it. That everything's added. Then there's also usually a constant bias. So you can have another number that is, again, associated not with any position, but just a global offset. And then the result of all this operation is a scalar number, and that goes to the center position in this new channel. The downsampling, the pooling, simply makes things smaller. So you take an input cube, again, x times y, some image size times the depth of channels, and you create something that has the same number of channels. So you do this separately for every channel, and you just reduce it in size. You just shrink it, typically by a factor of 2. And this pooling actually increases the receptive field. So it means that in the next level, a filter of the same 3x3 size or so will actually see a bigger region in the real metric space, in the object space, and therefore see the context over longer distances. If you do it repeatedly, the context gets even bigger. Moreover, the pooling creates a sort of an information bottleneck. It forces the network to abstract, because by going from the 224 times 64 here to the same with half the size, so 1/4 of the values, you actually have to shrink the information. You have to find a representation that is 4 times smaller, but nevertheless doesn't lose any important information. There's something in the Q&A here. Okay, so Nicolas Puccino asks, the convolutions remind him of discrete wavelet transform. One could use wavelet functions. That's true. You can, of course, use wavelet functions to filter an image. The point is that in the philosophy of the convolutional network is exactly not to predefine those filters, not to go and say, I use Gabor wavelets or whatever, but instead to learn those filter coefficients. So the unknowns of the function that you fit are the weights of the filters, which are chosen optimally such that they extract the right information. So you could use wavelets. If you do it in the first layer, it would probably not even make a big difference because those are very generic filters. But especially as you go deeper into the network, closer to the output, that's exactly the point of deep learning, of end-to-end learning, that you do not want to prescribe, basically handcraft how the values are transformed, but you want to learn from data in a statistical manner the weights that help you best to predict the correct outputs. Is that okay? Good. Okay, so the pooling, there are different ways of doing that. To continue, the most popular ones are either max pooling. So you go into this little receptive field that you want to pool into one number, and you just take the biggest one with the idea that you preserve sort of most of the information. You take the strongest response. You could also average pool. So you average all the values in there and say that's the mean representation in there. Or you could also do what's called a strided convolution. So that's basically just subsampling. You take every nth value, only every second value. You pick always the one at the top left corner, for example, and keep that one. This is, of course, in practice, then not, if you do that, it's not computed by doing all the convolutions and then picking some, but then you're, of course, clever and you already move the convolution filter with a step size of 2 instead of 1, so that you only ever compute those values, which you will keep afterwards. These variants, they can be used and interchanged, and it actually depends on the network design. It doesn't even seem to make so much difference which people use. Okay, and at the very end, after you've gone through all this, you do sometimes, if you want to predict just a single value or a few values, you can add a multi-layer perceptron. Somebody seems to have written something in the chat. Okay, that's good.
Well, that's me. No worry, that's me.
Okay. Okay, so we were at the point where we have a lot of convolutions and with some subsampling, and you can see this stepwise convolve, subsample, convolve, whatever, as a sort of feature extractor. You gradually abstract from the raw input into a more abstract representation, but one that is tuned to be good to give you a final answer, because it depends also on the output. You propagate through the whole network. So, or if you like, you can see it as a gradual transformation that very slowly takes the values of the input and step by step gradually transforms them into the output. And at the end of this, of course, you can have some multi-layer perceptron that then looks at everything and gets the global picture, especially if you just want to derive a single value for the whole picture. For example, what object is it showing or something like that. So you can see the last part then as a sort of the classifier, if you think in the classical setting, and the first part, the one that does more the convolutional filter type thing, is the feature extractor. But that is actually, that's more of a way of thinking about it. There is no clear boundary because it is really a gradual sequence of abstractions, of transformations. People. Sorry, here I was. That's the reason why people often talk of end-to-end learning. If you compare it to a classical approach of classifying or computing, predicting some numbers, usually what we do is we take the image and then we do some clever transformations. So we have some idea from our background knowledge of the domain, how we think we should transform it. Maybe we do edge extraction, or we compute a differential vegetation index or something like that. And then we hope that these contain the necessary information to predict our output well. Whereas here, we start from the raw values and we actually learn also that part, which is normally the feature extractor. So you don't have to do the feature extraction. You actually learn directly how to extract the features from the raw data and classify them through some final classification head. And people have tried to visualize these features, and you actually see that it really works that way. So here's a picture from Rob Fergus a few years ago, where you see that here at the low level, at the beginning, you really learn something that looks like Gabor wavelength, directional gradient filters, color contrasts. And as you go higher up, this is actually not the second, this is maybe a third, fourth, fifth layer, you see bigger structures, more complex structures that already look more like object parts. And then if you go even further, you get entire big pieces that already really remind you of world structures. Did we have another question? I somehow can't seem to get this.
Yes, it seems like there's one question. Can you read the question?
Oh no, it was Nicolas Puccino has answered. Thank you.
No, there is another question from Saif T. He asked that what is the difference between this approach and performing a PCA?
So at which point?
I didn't understand. I just read the sentences that he asked.
Yeah, I see.
Honest.
What's the difference between this approach and performing a PCA? I mean, a PCA doesn't learn any task-specific features. If you do a PCA, this is completely independent of what you want to do afterwards, of whether you want to classify land cover or regress the vegetation height or the density of the ice or whatever. So the PCA is agnostic. It's some sort of transformation that tries to not lose variance, but it is not a discriminative model. It is not targeted towards finding those combinations of the input that will help you best to answer your question. It could be that there is a lot of variation or a very small variation only, but one that is crucial. So if you have one feature that is, the general size, the image intensities are, say, around 100, but then there is one color channel which is always less than 10, 11 or 12 for something, and always a bit more. It's 11 or 12 for some feature, and then it's only 8 or 9 for the other. You would never find that. It's the first one that PCA would kill because it has a small variation. But if it's systematically linked to a certain answer, to a certain property that you're interested in, you should actually not discard it. So it's a different approach. PCA is more of a generative model that tries to represent, to compress the data, but it does this completely in an agnostic way without knowing for what purpose. And it would also be, PCA can actually, just to notice this before we go on, be used as a layer inside the network. If you believe you need a PCA, if you believe it's good to do this transformation into the main directions of variation, into sort of the spectral eigenvectors of the matrix, you can do that because PCA is an algebraic operation. So you can backpropagate through it. You could use it inside a network as a transformation. But so far, people have tried that. It didn't seem to bring much difference. Okay. Then let's continue. Where were we? Sorry, I've got a bit lost in my slide set here. Here we were. So I was showing a bit that indeed this thing learns features that intuitively seem to make sense to understand images. At the low level, they're closer to what we might have designed ourselves by hand. What's the color there? What's the direction of the gradient? What's the frequency of the gradient? But as you go higher up, it learns relatively abstract concepts that would be very hard to design as a filter and to know that these work well. Good. A specialty, something that I haven't mentioned so far, we said in the beginning, when talking about the MLP, the multi-layer perceptron, that we can actually put in not only multiple inputs, we can also generate multiple outputs. So we can generate a whole vector answer. And in the same way for the images, we can do that. So we can stick in an image, we can do this sort of convolutions and pooling and go on, but we can also have an output that is actually a raster. And in this way, we can directly generate a map. In geospatial engineering, you often need these predictions that take as input a raster, but they also take as output a raster because it's some sort of map or GIS layer, cartography and so on. And therefore, you can do that. So the way to either you completely don't do any downsampling, that would be the naive way, or you do this downsampling to get the context, but then you have some upsampling again. So at some point you think it's small enough, I've seen the context, and then you make the thing bigger again. You can imagine this is basically doing a convolution with a step size of 1/2. So you first upsample the image naively with some sampling method, and after that, you take a convolution filter to clean it up. And you can do this multiple times. What is usually important in geospatial engineering, if you take some standard CNN architecture that you've heard is good, is make sure it has enough skip connections. So that are these connections that take the values, these intermediate in representation, the features at some depth, marked pink here, for example, and copy them over past the bottleneck back to where in the upsampling process, you're at the same size, at the same resolution. By doing so, you make sure that you pass on the high frequency information that otherwise would be washed out and suppressed by the downsampling. So a lot of skip connections are usually important because in geospatial images, if you work with satellite imagery or so, the objects are small. It's not one sheep in a photo, it's actually hundreds of buildings in a photo, and you don't want to lose them. So you have to make sure the small details are not swallowed by this downsampling. These networks are really powerful and they're really data hungry. I mean, they are big. We're talking about millions, thousands and millions of trainable weights of unknown parameters, and they need a lot of data to learn those. I have some more questions, I think, right?
Yes, there is one. Oh,
How do the encoder decoder CNNs handle non-visible parts? For example, what's overlapped by a tree? Well, you cannot answer that directly in a way. It's like always, I mean, anything that we do in remote sensing usually is line of sight sensing, right? Okay, radar can penetrate a bit more, but in principle, optical, whether it's LiDAR, whether it's imaging, is line of sight sensing. We only see the first reflecting surface. What's underneath, we always have to guess. If you know that there are buildings and you want the buildings recovered, then you can actually have your CNN learn, because it can learn a prior, it can learn that typically the shape of a building, for example, is always rectangular or is always following straight lines or so. And then it may learn, if you train it that way, to complete them. So if your training data has not got no trees in there, but it has buildings which have the right shape, then this thing will learn to also in the output always generate buildings of that shape, because that's what it has seen. It should produce every time. Okay, and another question, is there any rule of thumb to estimate the number of training samples? No, because this depends on the complexity of the problem. There is no direct rule. Usually take a lot, take what you have. There's no reason to hold back. It's often more limited by how many training samples you can actually get. And when it doesn't help anymore, you will see it. So if sampling more and more and more doesn't improve the thing anymore, you would actually see the loss function during training just flatten out. It will flatten out and not get lower anymore, which means there's nothing more that this thing can learn, even if you show it more data. But more often than not, we have the opposite problem. We do not have enough data, and we have to find tricks for that. One trick is data augmentation. So you mirror and rotate and synthetically change the inputs a bit just to generate a bigger variety. You can also change the radiometry a bit, make them brighter, darker within reasonable scope or whatever. And then there is another one, and that's what's actually on the current slide, which is that if there's not enough training data, you can very often, surprisingly, use a network that has been trained on something else but related. So if, especially the lower level is very generic, it's really just what do images look like, and the mid-level is maybe what do remote sensing images look like, and only as you go to the high layers, it's really very, very task specific. So what you can do is you can take a network that somebody has already trained, or you have trained, depends, but can be somebody else, with a lot of data. And even if that was for another task, if that was maybe for plant cover classification, and you use this one for vegetation sensing, it might work because it has seen a lot of vegetation and it has a lot of information already imprinted. And then with fewer data, you can what they call fine tune, so train it further from an already very good initial value to work well for your task. And this works not always, but it works surprisingly well. I've even seen cases where you have actually pre-trained on close range terrestrial images, and nevertheless the network works then very quickly works well if you train it for radar. So it's quite surprising. Okay, I get a lot of questions now. I'll try to answer them.
There is also one question you might miss, like Nicola's question about Sentinel-2.
Yeah, if we use multi-source, multi-scale imagery, Sentinel-2, and some hyperspectral, do we have to make the spatial resolution match? Well, I mean, this is a general remote sensing problem that's not specific to deep learning. You have basically two different ways of dealing with it in deep learning. Either you take the lower one, the lower resolution one, and just sample it up, although you know that this is not gaining information, but it also doesn't hurt if you do it right. And then you concatenate it and you work at the higher resolution. That means, of course, that this one is in reality only contributing to the decision, to the output at its lower resolution, but that doesn't matter. You're just making it sort of conformant to fit it in the network. There is another way you can generate a multi-branch network. So you can basically make a neural network, a convolutional neural network that takes the high-res Sentinel, and another one that takes the lower resolution hyperspectral. They are separate branches, but they meet somewhere. So the one on the Sentinel one has maybe more downsampling, and then when it has the right resolution, these two branches meet. They're concatenated, and from then on, pass through the network together. So you can actually have multiple inputs dealt with separate weights so that they can have different size. That is possible. You can even do it with the same size. That's, for example, what happens for stereo matching. You take the left and the right image, you pass them through two branches. These two branches but are tied to have the same weight, so they do the same thing to the images. And then you correlate those outputs before you go on through the network. Okay, this one I think I answered. There were some others here that I've somehow lost. Is there any rule of thumb? Follow up on the non-visible overlap, the radar. One more. A question regarding segmentation, pixel classification. In the tutorial, usually the label image is fully covered with data labels, but what if we have a limited number of training labels? So the solution, if you have sparse training data, if you have training labels, but they don't cover all the pixels, they're only at some of the pixels, is usually to do the prediction, to design the network such that it outputs still a label at every pixel. But what you're going to do is compute the loss only at those pixels where you have an output. So you compute the loss function only at those pixels where you have an output, and the others where you don't know the answer, you simply mask them out. Okay, then let's continue. We continue from the point of what if we don't have enough training data? We said we can do data augmentation and everything, but this thing with using pre-trained networks, initializing with weights that are already reasonably good, this works very well, and this was actually, and still is, a big success factor for deep learning. The people who do this, many people who do this come from the computer science, open source research world, and they share their network. So when they manage to design a network that works really well, they put the specification of the network, the file that defines its architecture, on the web for everybody to use. So you don't have to redo the engineering, but they also put the set of already pre-trained weights from their problem on the web. And this means you can download it and then start from there to build your own network and to train it. And this practice of publishing and sharing your computational systems really was an important factor and pushes the research. It makes research and also uptake in practice much faster because you don't have to re-engineer, and you can always get some decent weights for many problems. It's a bit harder if you do something exotic like radar processing where not many people work. But as I said, even there, if you take the trouble to train a network, then it's of course also considered good practice to then publish your weights so that the other ones can also profit, at least if you're not at a commercial company. I showed you this example network before. I'll show it again. That's called VGG after the Oxford Visual Geometry Group. It was one of the first super deep networks with, I think, 19 layers or 16 in the smaller version. And I show it mainly to make clear how many parameters we have. So people, if you're thinking classical statistics, this should actually not be possible, right? This has 13 3x3 convolution layers. So there's more than 14 million unknown weights. The pooling doesn't need any weights. So that would be common for anybody who uses this architecture. If you use it for classifying things, then it has another 3 fully connected layers, and these have more than 100 million weights. So we're talking 100 million unknown parameters in a function. Of course, these are not uncorrelated, otherwise it would be impossible. And of course, the structure of the network regularizes them very strongly. They're not 120 million real degrees of freedom. But nevertheless, this network can actually be trained. Takes a few hours, of course, but it can be trained. And this goes a bit against, there we have to switch our brain. This goes a bit against what we learned in classical statistics. Classical statisticians tell you, and we learned that in parameter estimation as surveyors, you should not have more unknowns than you have observations. You should have fewer unknowns than observations so that you have redundancy. And machine learning works a bit different. Their approach is more, you take a very, very complicated function with way too many unknowns, more than you can ever have observations, but you regularize it very strongly. You build in biases into the model that tend to make it simple and make the parameters small or make some of the parameters disappear and tie them together. And then you take this very complicated function and fit it. And by having the regularizer, it will only make it as complicated as really necessary. Mind you, these models can overfit. It also means you have to control them because other than a linear regression, this can overfit. This can overfit, work very, very well on a small training set, and then not work well when you apply it because it's fitted to some ludicrous detail in the training data that is not representative of other situations. That's why we always, in this context, use validation data. You never look only at the error and say, okay, the loss function, the error on the training is going down, so I'm fine. In parallel, every few iterations, and the frameworks have that built in, you always also evaluate it on validation data, which means on data where you know the reference answer, but you're not using it for fitting. And so it's an independent check how well this generalizes. Here's a little add-on, just for those who might be interested in time series. So if you want to process time series, sort of have recurrent events like a temporal filter, Kalman filter or so, there is a version of neural networks that can do that. What they do is basically they add a new time step. So if I evaluate it now, and then I evaluate it again for the next picture in the time series in a video or so, I input not only the observation, but I also input the hidden state. So sort of this intermediate representation of the previous time step so that you tie them together so that this latent hidden representation evolves over time in an autoregressive manner. It looks backward and sort of takes the previous one into account too. So this is then like a temporal filter. So you see this here, it's a bit more complicated. You take the new input that has its set of weights, but you also have the old hidden state from just before with another set of weights, and all these are combined. There are more complicated variants of those that also have some memory, so they have some gating to sort of modulate how strong you weight the previous state and preserve it, whereas how much influence you give the new data that you see to modify the state. I'll just mention them. We don't need to talk about them in detail now. They're called something like generalized recurrent units or LSTM, long short-term memory, but they're very valuable for time series analysis. Okay, I have some questions again. I will answer those before we go on. Jesse Buyungo, can I train my image segmentation network on a data set like Toronto and then use it to do segmentation on an area elsewhere, for example, in Uganda? If not, how can I design my own training and validation data set? So what I would do is train it first on a large data set that you have. Well, if you have a big enough data set in Uganda, you're sorted. You just train on that. It's better the closer you are, not necessarily spatially closer, but you need to train on something that has a similar statistics, a similar content than what you test on, because the network is in the end still just a regression or classification engine. It just learns by heart and basically interpolates. So it should be good to have training data that is from nearby or from similar conditions. If you don't have enough, I would nevertheless, again, go with this pre-training strategy. You download some big data set, some Earth Vision Challenge or Toronto, so you train on this. And then afterwards, you train with the smaller amount of data from your local environment to fine-tune it. That fine-tuning, to say another word, is actually usually done in stages, or can be done in stages. So what you can do is, for example, first you leave the lower levels of the network, the ones that are basically just the image filters at the low level, unchanged. You don't change those. You only update the end, the stuff that is close to the output. That's because maybe your class set, your nomenclature, your desired output is completely different. And so the other network is a very bad representative, whereas for the low level features, they will be similar. So you only update the top ones first, and then gradually you release more weights until you've trained the whole network. Because if you start immediately, you might actually destroy your low levels because your high level information is so badly matched. So you can also do this in stages. Another question, Mig Lagerhit. Data augmentation as an option to densify the training data. Reasonable combination of augmentation techniques. Again, there is no rule of thumb because it depends on your problem. It depends on what you want. Often in overhead images, rotation by any angle is relatively acceptable because the rotation, there's no inherent direction, but sometimes it might not be. If your images are from a specific city that has a very directional grid layout, then you might only want to rotate by 90 degrees so that you don't train the network for something that it will never see and that it should not do. In close range images, if you're working on close range imagery, say from a robot or from a mobile mapping system, you might not do rotation because you don't want to train on images where the sky is at the bottom and the road is at the top. Scaling might make sense in many cases, so rescaling so that you cover a bigger scale range, but you do not want to do that in a satellite image where you know that the ground sampling distance is completely constant and will not change. So it really depends on the situation. You have to think about what are the allowable transformations, the ones that are plausible to happen in my data and to be normal there, and not apply transformations that create something that's out of sample, that is not out of distribution, that is not even interesting for your problem. An anonymous attendee says classification of images. Where's that gone? Classification of images are usually done in RGB images, 3-layer. Would the concept also work in hyperspectral? Yes, it works in anything. You just have to train it. All that changes is how many input layers you put into your network. We have actually used these things with hyperspectral. You, of course, have to change the architecture to have a larger number of input channels, multispectral or hyperspectral. But for example, when we work with Sentinel, we just put all 13 channels in. You can use the rest, reuse the rest of a classification network, at the very least, at the first stage. You have to make more weights because you want to filter over 13 channels and not over 3. But it can be done. The system itself doesn't prescribe how many layers there are. This RGB is just because normal computer vision people take pictures from the internet and they are in RGB. But it works equally well if you have a 4th channel with an infrared or if you have a multispectral or a hyperspectral. Of course, always being aware that the hyperspectral signal is extremely redundant. So, but you can still use it raw. Recep Khan, if the architecture learns roof shape, but the roofs are not the same everywhere, can we say we have a generalization problem? Yes, of course. Like with every statistical learning engine, like with every machine learning system, if you train for a specific situation, so you're asking the network to, or if it's not a network, it can be a normal classifier, but you're asking your machine learning algorithm to learn the specific properties of your training data set, and then those are not there in the test data set, then the thing will fail. That's sort of the art in a data-driven setting to make sure you represent your test area correctly in your training data. So you will see this, of course, if you train on roof shapes that are different because they're in a completely different building style in another part of the world, then it's not going to work well because it will try to make things that are not there. Farina de Waard, can you maybe at the end of the talk recommend some good sources for finding pre-trained RS data? Usually just use Google search. I don't think there are any hidden dark web opportunities. Usually either it would be public and therefore findable by a search engine if you browse a bit and check a few keywords, or if not, another way is just use your informal network, access your colleagues, ask at space agencies, at universities, at whoever. If the people have data that they're prepared to share, then they will probably not say no. If they say no, then it's data that you wouldn't have gotten anyway. But there are quite a few around. I don't know, they're not as many as for normal images, but I think you can find several different ones. Or email people who have published something, who have used the network for something that seems to be a good resource for you. They might be able to share their data if they have not already done so. There is, of course, also a caveat to this sharing. One shouldn't go too far. It doesn't make sense if you have a good reason to believe that you should use a different architecture, that it's better to design your network structure in one way or the other. You shouldn't step back from that completely and change your network layout in a way that you think is detrimental just so that you can use some pre-trained weights. So that's always weighing your options. In many cases, the standard architectures for which there are weights are good enough. But if you have a specific problem where you cannot use pre-trained weights because the whole architecture is completely different, you might have to do with that. Burak E, is it possible to create a new worldwide usable application? Each region has their own standards like Corine in Europe, so would class spec suits with other standards? I mean, I don't think this is a question that has to do with deep learning. This is a general question of standardization of will people ever agree on a standard that is useful worldwide, or do they have, for either political reasons or for scientific reasons, decided to make different nomenclatures? And if the nomenclatures are different, you have to adapt to that, and you have to work locally where this nomenclature applies because it doesn't help the others. I wouldn't say this has anything to do with deep learning. I mean, even if you use this with some good old standard classifier, if two jurisdictions or two local regions decide to use completely different class sets, then there's not much you can do for them except the translation table. Okay, so we were at the recurrent networks. I want to say a few more words about those. Those are particularly useful for time series analysis. So in remote sensing, we have these issues, as you know, for example, crop classification. If you want to do crops, the important thing is not what does it look like in one picture. There can be a lot of confusions, but what helps a lot is to follow things through their vegetation cycle, through their seasonality, and see how they evolve, how they develop. Field crops are often one-year crops or half-year crops, so they grow, they cover the ground, they get bigger, get more active, then they dry out, and they're harvested. And this will actually help you. And then you want to analyze time series. And there, for example, recurrent neural networks would be a very good candidate and have already been used. Other monitoring tasks, change detection might be useful if it's over more than just 2 or 3 images over longer time series and you want to follow a development. So whenever you have this, then the recurrent neural networks might be a good resource because they, of course, save parameters. Since at every time step you use the same weights, they're easier to train than if you make a massive temporal convolution. They are, however, recurrent networks are a bit more difficult to train in general. Takes a bit more fiddling and trying because they are numerically a bit less stable. This has to do with the gradient propagation through the long time series. If you want to work with recurrent networks, it might be a good idea to look in literature on other specializations. For example, people dealing with text analysis or music analysis and so on, they tend to work more with those, and there might be more expertise there than if you look in the remote sensing papers. Okay, with this I'm through the lecture, and I think timing-wise we're in a good place. I just have a few examples that I show you to make this whole thing a bit more concrete. Many of you might have their own examples, which might be more exciting, but since I wasn't sure, I thought I'd just show a few that illustrate what can be done. We had land cover. Here is an example for a combination of close range and overhead. This is mobile mapping data mostly, and the point is to classify the tree species. So you see this panorama on the lower right. You might have seen things like that in Google Street View or wherever. And this exists in many places, so it's a lot of valuable information, or it can be captured with a mobile mapping vehicle with relatively little effort. And in this case, it was important to say, what is the species of every tree on the public ground next to the road? This is important for managing them if you don't have a proper map or tree cadastre, because different species have different needs, they react differently to draft, they have different age where they need to be replaced, and so on. They might be susceptible to different pests. Possibly also other parameters, what's the tree trunk diameter, breast height, and so on. And so we used these images, these panoramas. We knew where the tree was. That was done in a previous step. So we had a detection where we knew where the tree was, and we could then, for each tree, take images, an aerial one and also a street view one. And that street view, we zoomed at 3 different magnification levels because the distance to the tree was not very accurate, and we weren't sure we were getting the scale right otherwise. And for each of these, we pushed them into a neural network that was actually based on this VGG that I showed you. We trained this on a data set of trees that had been labeled by experts, botanists in the field. This was an application in California, so these were people from Caltech. We make 4 predictions over which class of tree is this, which species, and then we do some fusion. There is a trick, there's some fusion of these 4 separate network outputs into one. That was just a technical trick because the network were too big and we couldn't put all 4 on the same graphics card, so we couldn't train them together. And this classification then told you if you saw a certain tree. Now this is a Mexican fan palm, or this is a live oak, or this is a holly oak, or a southern magnolia, or whatever. You see some examples here of the more frequent classes in Los Angeles area. And this was actually for 40 classes, more than 80% correct, which we found quite surprising, because even the labeling by the experts sometimes had some issues with species that look similar. Another example, this is not from remote sensing, this is from cartography, to give a bit of breadth and not pretend that we need this in geospatial engineering only for remote sensing. You know that cartographers are very picky about having very nice, visibly pleasing graphical representations, especially of the 3D relief of the shading, so that the maps have a plastic visual feel to them. And this shading, to generate these shadings by computer is relatively difficult. If you just naively sort of virtually shaded with the light, it often doesn't look quite as convincing, especially in printed maps, but also in digital maps. And so the cartographers here at ETH did an experiment where they took hand-drawn, expert-drawn relief shading of mountains. You see some here on the right side, and the corresponding digital elevation model. And they trained a network that if you show it the elevation model, creates a relief shading. This is a bit different network with a lot of skip connections. As you see, it's called a UNet architecture. So it has progressively always downsampling, but also passing on to the output scale so that all the high frequency detail is kept. So here in the bottleneck, it's only 20 by 20. It's lost all the spatial detail, but that is re-injected via these yellow arrows. And here you see an output. So this is an example of an input DM. If you analytically shine a virtual light on it to create shading, you get something like on the top right, which is okay-ish. But for a printed map, way too unsharp. A real manual expert thing still looks best. That's the bottom right here. And the bottom left, this here is the CNN generated shading. So you see it's somewhere in between those two, but it's actually relatively close to the human expert design. This shows you in a way also that it's a bit a low-level imaging thing. It's a clever image and image transformation tool, because this is not an analytical transformation. This is basically just trying to mimic the contrasts and the drawing sharpness and so on that the humans typically put into their shading drawings. Okay, here I get a question in between. I'll answer that. Gali Abdulali Abu Bakr, please ask the question again in the Q&A session. We're almost at the end, and I think it fits better there. Here is another example. That's a typical remote sensing example, although a difficult one, which is to map vegetation height from space on a large scale. So not in a photogrammetric way by triangulation, because we don't have stereo at this large scale, but we just took the Sentinel-2, so that's monocular imagery at 10-meter GSD. And the question is, if we somewhere have ground truth for how high the trees are, this ground truth could, for example, be from a LiDAR campaign, which could only be flown locally because it's very expensive. Can we learn a network that takes the 13 Sentinel bands, all 13, the whole data cube, because we were talking about more than RGB, sticks it into a neural network, and what the neural network outputs is a map of the tree height, continuous height value for every pixel. And we've done that on the large scale. This, of course, needs some compute power, so this computes several days, even if you have a little server with a dozen GPUs in it. But we could do this for large countries, as you see, entire countries of hundreds of thousands of square kilometers, and at 10-meter resolution, which we think is still a world first. And it works fairly well. It does saturate at some height. So for those who live in the places with the highest vegetation, there's bad news, because at about 55 meters height, we found that it saturates and you can no longer monocularly guess the tree height. But it's actually quite surprising that monocularly, by looking at a single image without any direct depth cue, you can estimate whether a tree is 40 or 25 meters high. As a human, it looks very difficult, I'd have to say. Okay, a more photogrammetric application, even DEM filtering. So we took a photogrammetric DEM this time, but one that was taken from space, from world view images. So it's fairly noisy. You see it here on the outside. That's what it looks like. This is done with a state-of-the-art semi-global matching pipeline. So this is not because we just mishandled it, but because you're at a rough GSD and with suboptimal lighting as you get it from satellite images from different days. And that's what matching gives us. And then, but for specific places, especially for my hometown of Zurich, we had a very precise city model from the city administration. And we used that as sort of desired output and trained the deep network to take the rough DM and the image data. So sort of the ortho-rectified image data, ortho-rectified, of course, with the mistakes. So you do see displacements, which give you a cue what to improve. And then as output, create the cleaned up DM. In this special case, it also includes a vegetation filter, because our ground truth, our reference DM, is without the vegetation. So all the trees are actually cleared out. The network learns to remove them. I have a little video there. I don't know whether it plays via Zoom, where we're showing first the input and then how it's improved by the filtering, by learning with the deep network how to transform the raw height values into more realistic ones without spikes, with increased detail, and without the vegetation. So I'll let the video run a bit. I don't think we're in such a time hurry. Okay, with this, I'm at the end of the lecture. I think timing-wise, we're almost spot on. To quickly summarize, I did a basic elementary introduction into the background of neural networks. So the perceptron is the most basic sort of classifier that you could frame as a neural network. And then the multi-layer perceptron, which is sort of the first real deeper network, how to make it deep, how to use the convolution trick to make it amenable to images and also sound and other data where this convolutional structure is present. And I briefly mentioned recurrent networks at the end. And we talked a bit about the technology, how is it built, but also how can it be trained. And maybe to put this a bit into context, as in general, deep learning way beyond our application field is really a high-end tool, one of the high-end tools for complex data analysis. And actually the biggest success stories where it works the best are really almost sound and images. So we are in the right field. They do need a large amount of data. They do need a lot of compute power. Luckily, these things are nowadays available to us. And in practice, they're very powerful. The theory of them is much better developed than it was 5 years ago, but still many things are poorly understood. It's one of those things where we have very little rigorous mathematics to tell us why things work because they're so complicated, but empirically they work really well. And there are some sort of intuitive hand-wavy mathematical reasons why, but some development is waiting there for the theory people to really explain what's going on. Okay, thank you. I think we can switch to the Q&A with that. Shall I start with the questions that are already there?
Sure, there are 1, 2, 3 questions. Of course, you can start the question and session.
Could you please tell us about Python machine learning libraries for geospatial data? So I wouldn't be aware of anything that's specific for geospatial data. One would simply use PyTorch, which is sort of the standard deep learning library that sits on Python. And the geospatial data is in the end not so special, right? I mean, it might have 16 bit depth, that doesn't hurt. Python has a full sort of programming language built in, so you can do your type conversions. And actually, for deep learning, you would anyway convert it to, usually convert the data to floating point numbers, so it doesn't matter what the radiometric depth is. You can program the things yourself. You have, of course, the deep learning network, it only does the deep learning. Everything that is around that in data handling, tiling up your image into overlapping tiles that are small enough to feed them if you have very high resolution and so on. This is something that still rests on you to do. But actually, Python has a vast amount of libraries for all sorts of things and a relatively intuitive, simple scripting interface. It's a quite comfortable programming language to work with. And many people prefer nowadays to work with Python and not, for example, with MATLAB or so. And certainly, it's easier to handle than writing proper C code. So I wouldn't be aware of any specific libraries. There might be some, but for deep learning, for machine learning, you can simply use scikit-learn and NumPy and PyTorch and the usual tools. Okay, somebody's asking about SAR data. It depends on what type of SAR data. I have so far own experience only with amplitude data. So throw away the phase, take a ground range corrected amplitude in different polarizations, then you get an image with 2 or 4 channels. And that you can handle with a neural network. The theory says it would not be optimal because the noise structure is different and everything. In practice, we found it to work really, really well. I don't have a huge amount of SAR experience in deep learning, but we've used it, for example, for detecting the lake ice, so the frozen or non-frozen state of the alpine lakes, which is a part of the essential climate variables. And that works very, very well by just simply taking the amplitude data, taking some pre-trained network, training it to recognize whether the pixels are frozen or not on the lakes. So that's what I would say. I guess when it comes to phase, you might also still be able to treat it in that way, although it's circular, so the filters might also not be optimal. I think to build something that is specific for SAR data, that really deeply takes into account the nature of the radar signal, that's an open spot. That's something that might be missing. So far, those people who needed something with SAR have not done it because they got around without it. But it's indeed true that a really SAR-specific deep learning approach is something that's reasonably principled, that takes into account the physics and the statistics of how SAR is generated. I wouldn't be aware of that. But in practice, you can just stick it in as an image and it will often work. Okay, following your example on tree type classification, would it be better to have one network model to detect varying objects or multiple models, each dedicated to one specific object? No, I think usually it would be better to have a single network for multiple. That depends, of course, the network has to be big enough. It must have the capacity. the amount of parameters to be able to solve this more complicated problem, but it can benefit a lot from doing multiple classes in one network, because there is feature sharing. There are actually correlations between classes where they might have similar structure. So overall, you will gain by treating them together and using that redundancy. That it's also better because you can learn to discriminate better. If two classes are hard to distinguish, so they're easily confused, then if you learn a separate classifier, one for the A and one for the B, they will often give the wrong answer because you've never told them to keep the two apart. Whereas if you put the two in the same network, you're explicitly telling it not to give it the other label because that is penalized by the loss. So you're playing more in the spirit of a discriminative function that tries to find the decision boundaries also for the harder cases. Farina Devad, very general question. Can we get access to your presentation slides? Yes, you can. There is probably only a preliminary version at the Student Consortium. I will make a PDF and email it to the Consortium board after the presentation, and then they can make it available. Matej Racic, what's the biggest shortcoming of deep learning for remote sensing? I mean, its biggest shortcoming in general is hard to say. There are still some things it cannot do very well. For remote sensing in particular, I would dare to say one of the biggest problems is the scarcity of training data. Big organizations have that, but small players don't have it because it's just so much harder to generate than for general purpose robot vision. There might also just be smaller financial incentives. The car makers have huge databases of images because building autonomous cars is a big business compared to remote sensing. But, well, and it depends. It's horses for courses. You should use deep learning if what matters is predictive accuracy. If what matters is that your prediction, your map is good, correct, useful, then deep learning is a good tool if you have a lot of data. If you want something that generalizes really well from one place on Earth to the other without having to recollect training data, then you should, of course, use a model that cannot overfit so much. Then something more physics-based, a model with a stronger physical component, with a stronger sort of location invariant, non-statistical backbone would certainly be preferable. And another thing is, of course, computational power. If you want to do something worldwide, we are thinking about such things. We're preparing for some applications where we really want to process worldwide, but then you basically need friends who have cloud computing power because you need so many GPUs. Moin Zohari asks, can we talk about recent advances in unsupervised learning? Is it transferable to remote sensing and photogrammetry? So my first answer, without knowing which advances you particularly mean, would be yes, because I believe that technically speaking, not in the application, but in the technical handling and algorithmics, remote sensing is in a way just a specific form of computer vision. So if it can be done for normal images, I tend to think that it can, with a bit of adaptation and cleverness, also be made to work in remote sensing. Unsupervised, I don't know of so many things that are completely unsupervised and really strong. What is a trend, and some people call that unsupervised, is what others call self-supervised or so. So to have a supervision that is not generated interactively, but that uses some plausibility constraints, like that left to right and right to left matching must be the same, or circle constraints must be held. So if you transform A to B and B back to A, then it has to look like A again, and so on. So this sort of self-supervision that is implicit in the problem and doesn't have to be created by hand, that certainly could be useful also for remote sensing if you find an application case for it. One where you have it. One that is well known, for example, is stereo matching. So there in stereo matching, training not on hand-created or LiDAR-created depth maps, but instead training on transfer error, so on the fact that left to right and right to left must work out, has already been shown. It doesn't work quite as well as if you have super good ground truth, but of course it can be trivially done without having the depth. So Paul Magden, can deep learning be used to label unstructured point clouds, identify buildings? Yes, it can. We didn't talk about it, or I didn't talk about it in this tutorial, but there are extensions to 3D point clouds, which now work very well. There are basically three structures. One go under the name of PointNet or PointNet++, which take a sort of a small multi-layer perceptron over a point neighborhood, and then some per point treatment, and then some max pooling or average pooling, so that the ordering of the point becomes irrelevant and you're not order dependent, and those hierarchical. There is the voxel world, so you basically do 3D voxels. You voxelize the point cloud in some reasonable manner, and you then do something like 2D convolution in 3D. This needs a lot of memory, but it's feasible. And maybe the most elegant one and most recent one is to do the convolutions, to approximate the convolution in continuous space. So convolution is not only defined on a raster. You don't have to think of it like an image filter pixel by pixel. You can do it between continuous functions. And that means you can take a function, you define this function. Obviously, it's defined only on certain places. So you have to find a number of points in some ball and then interpolate in between them. And you slide that ball through the space, you place it on the individual points and compute the convolution over its point neighborhood. These go by names like PointConv or KPConv. And these methods now work really well. We've tried on mobile mapping data, for example, also on aerial data. It is a very strong tool. It is computationally a bit less efficient. It's a bit slower. It needs a bit more space with its 3D data, but it does use the sparsity very well nowadays so that it can be run on normal computers. And just look up 3D point cloud neural network in the scientific literature, and you will find a lot of practical things, including code on the web. So you can download existing networks. Simple, quick question. Unsupervised clustering, K-means, is it considered machine learning? Yes, it's considered machine learning. It's considered unsupervised machine learning. We can use it to segment images, but we cannot use it to label them as such because it doesn't give labels. There is, of course, this school of unsupervised segmentation, but that is really clustering. You form clusters of things that look alike, that seem to be the same thing. And then afterwards, after the fact, the operator looks at it and says, okay, this is this and that class. So that can be done. Of course, there is no guarantee that you get the right classes because K-means or any clustering technique, spectral or whatever, will always find the things that are naturally grouped together, that form classes in the data. And that needn't be exactly what you're after. It can be that you have a class that actually is distributed over two clusters and might be very hard to distinguish from another one, have a very narrow boundary. And those situations it will not be able to resolve so well. But of course, it is machine learning, but unsupervised learning, which is its own branch, which includes density estimation and clustering and these sort of things. Another question from that person, branched neural network for multi-scale imagery. What is the formal name of the architecture? There is no formal name. Some people call a network with multiple input branches that have the same weight. So you can have two input branches that separately take two different images or layers, but they are forced to have the same weight. So they're just basically clones of each other. And these are called Siamese networks after the Siamese twins. But if they have actually different weights because they're for different modalities, for example, I wouldn't know what to call them. Mind you, it's not always necessary to do this. Very often you can actually just stack the modalities on top of each other, and that would give you the potential advantage that you can extract correlations between them. So there can be filters that take part of the values from one modality and part from the other and combine them. Whether that is useful in practice or you prefer to split them if you, for example, have scale differences just so that you don't have to upscale and make a lot of unnecessary parameters, that's an empirical question. As many things, the engineering of neural networks is empirical. Before, when we did not have end-to-end learning, we had to sit for 2 weeks to design good features, and then the classifier was easy. Now we don't have to design features, but instead we have to design the network. That also takes some effort. Nothing comes for free. Lagahit, final question. In my results, I always get very small misdetections, often the size of a pixel or so. Misdetections of what? I'm not sure what this refers to. I'm sorry. Urvi Schroff asks, can night vision remotely sensed images be used for feature extraction using deep learning approach? Any images can a priori be used. I think if it's taken with a camera and has this convolutional structure, nothing speaks against using it with a deep network. Of course, you might have to retrain the network a lot or from scratch because the statistics of night vision is very different. But I don't see why one shouldn't be able to apply it. Farina de Waal asks, have you worked with Google Earth Engine to have more computational power? We have worked with Earth Engine. However, the integration of deep learning into Earth Engine is not very convenient at the moment. It is just about possible, but it's not extremely convenient, which is due to the large-scale software architecture behind it. So we tend to do the deep learning outside of Earth Engine. And actually, if you do it on Earth Engine, what Google internally does in their data center is they write the data out of Earth Engine, run it on their normal machine learning service cloud, and then pipe the result back into the Earth Engine, because inside Earth Engine, they cannot even run it. But in principle, I'm told it should be possible. We have not done it though. Moin Zohari says, following the response on Multipro, one model in whatever DSTL, I don't know what it is, contest, the first 3 winners were using separate models for each class. I mean, I would say that depends on what the task is. If the 3 classes are very different and very specific, then you're of course simplifying the problem by just saying, don't try it, look for any correlations that are not there. If one thing is to detect, I don't know what, buildings, and the other thing is to detect ships on the water, then there might not be much to share and there might not be much confusion. So it's of course easier than to train a smaller model. So that depends on the situation. But if it's really this object detection scenario that I imagine, for example, in mobile mapping or in the city where you have to find all the street furniture, I would rather recommend to do all in one, but it depends on the situation. That's a general thing in data science and machine learning. The most important thing is to think in advance, what is it that I'm modeling? What's my problem? Where are the difficulties? Where are the sort of beneficial parts of this problem? Where do I have data? Where do I not have data? To plan very carefully and to model carefully and try to set the problem up in the right way. That is more important than whether you use deep learning or random forests or what other tool. The tool can be part of the planning, but if you use them in the wrong way, then also powerful tools will not do their job. Regarding the DM improvement, to improve the DM, are you using as input the DM generated with SGM? Yes, we're using both the input, the SGM DM and the stereo images. That was what makes this work a bit different from pure stereo matching, that we make the work of the deep network a lot easier because it gets an initial DM that is already reasonable and it only has to learn to clean it up, but it doesn't have to learn stereo matching from scratch. So for MigMig is following up to follow up on the question. For example, I'm trying to detect a certain lane marking, a road arrow. The network works great and detects the marking, but a pixel that is not even a lane marking gets misdetected in an image. Often it's just one pixel or so. I cannot remote debug this. If it's really just one pixel or so, then it's probably also not a problem, but I don't know exactly what's going on. And of course, there is a tendency, depending on the architecture, to slightly over smooth, to make a bit too blobby or a bit too big the detection. This has to do with the downsampling and the big context. That always means that you smooth your output a bit, like it or not. But in this particular case, I really don't know it, and it might, I don't know. Now I can't say anything without seeing more of the problem.
Okay, so I think there are no more questions, or okay, so there are two more questions, Dr. Conrad.
Okay. How is noise handled in 3D airborne point cloud data using deep learning? I mean, it's not handled explicitly. It depends. If you want to, if there's a particular type of noise that is always there, then every example that you show to your learning engine will have that noise in it. So it will get used to it. It will learn that this is the normal type of noise, and it will hopefully digest it because the answers don't depend on the noise. So it will see that this is an irrelevant part and not the signal. But you don't do a special treatment for noise. If there's point clouds in there, you'd run at every point. And obviously, for example, you can teach it that. You can even presumably build a filter. If you have a class that says this is an outlier, this is a noise point, and you have those labeled in some training data, then it will learn to filter those out and give them that label.
I think there is no question anymore. Then I think, Charm, you can start your talking.
Okay,
Thank you, Conrad.
so yeah, so again, thank you, Dr. Conrad Schindler, for a very interesting topic. And we have answered a lot of questions during the lecture and, of course, after the lecture. So, a few reminders, a few announcements before we close the session. So, the recorded version of the webinar and the slides will be available. So, we'll send to you the links and the slides. And of course, the evaluation form will be sent to you. So please complete the form. We'd love to hear feedback. And of course, it will help us to improve the organization of the future webinars. And another webinar will be organized sometime in May. So please check them out. So we'll post our announcements in our social media accounts. So thank you for being here, and maybe I would like to request a very short message from Dr. Schindler for our students who are present over here. So especially to those students who would like to pursue more in the deep learning and machine learning topics. Dr. Schindler?
Well, I don't really have any special message. About deep learning, what can I say? I mean,
Maybe to the students?
Don't be afraid of it, and don't be in awe of it. It's just another technology, a very good one, a state of the art for many things, but it's just another technology. It's no magic. Don't forget all the other things you've learned. Use it wisely. And on the other side, don't be afraid of it. If you want to use it, it is no black magic. Many people have learned to do it in a couple of weeks, and you don't need to be afraid of it. You just, have to put your head to it, go on the web, do a few tutorials, program a little bit yourself. We couldn't cover this here, but there are a lot of good resources. Learn how to use it. Importantly, don't become a pure hacker. That is dangerous. Learn how to do it, but try to, in the background, always learn a bit of theory. Try to understand what you're doing behind the programming commands. But yeah, just treat it reasonable. Treat it as the currently best technology for some things that we have to do, but just one more technology, and who knows what comes next, or what it might not be suitable. But in general, it's good if we get new and more advanced methods that help us solve our problems. So that's actually all I have to say about it.
Thank you, Dr. Schindler. So one more thing. So actually, we featured Dr. Schindler in one of our newsletters. So maybe we'll share also the link of that newsletter. So we interviewed Dr. Schindler there.
That's
Okay,
years
so
ago.
yeah. So Mustafa, do you have anything to say?
I can say thank you, Dr. Shina, for your amazing lecture, as well as the answering the questions. We are really delighted to listen your lesson. Also, thank you everyone for your participation and interesting question. And I'm not sure we can list or such question, but definitely we will share the recorded webinar on YouTube channel, as well as we will share the presentation afterwards on Student Consortium webpage, as well as on the social media channels of ISPRS Student Consortium. So that's the whole thing I can say right now.
Okay, so thanks again for joining us for today, and we'll see you next time.
Charm,
you.
a short
Yes?
question. Should I send you the PDF of the slides?
Yeah, sure. Yeah, and we'll,
Because I mean, the recording from YouTube is probably not as good in quality if people want to look at it.
yeah, so we'll share the slides as well to the participants.
Yeah,
Okay,
thank you.
Thank you.
good. Bye-bye.
Bye bye,
Bye-bye.
everyone. Bye bye.